Hi, it's Gary, and in this video I want to bring you something a little bit different. This week I had the pleasure of giving a guest lecture for the Physics of Music course at Wake Forest University, which is an interdisciplinary type of physics course designed for undergraduate non-physics majors, bringing together the worlds of music and physics, which is a perfect combination because, as you know from the Lutherie Demystified series, we talk a lot about how physics rules what we can do as guitar builders. And so I wanted to give a flavor of how what we do as guitar builders is constrained by the laws of physics, but also bring in some ideas of how luthiers work with guitarists to build an instrument that works for not just the player, but the audience, and also something that a luthier can actually accomplish within the rules dictated by physics. So you'll hear some ideas that we've presented in past episodes of this series, and then some new material that in future episodes of Lutherie Demystified I'll actually talk in more detail. So I want to thank Dr. Jack Dostal of the Physics Department and Dr. Marco Sartor of the Music Department for the kind invitation, and the Interdisciplinary Arts Center for making this talk possible. So I hope you enjoy it. Hi, it's Gary, and I want to welcome you to my workshop. I'm in New Jersey right now, about 20 miles west of New York City, and we're going to have some fun. I want to share with you something that you've probably not been exposed to. Even though guitars are very popular, you've probably not been exposed to how they're built. And guitars can mean a lot of things to different people. To the players, it's a means to express something that is not able to be expressed through words or pictures, but only through the magic of music can you express something so deep. And a guitar is often a tool for that expression for their artistry. In terms of craft, some people view a guitar as a work of art, although I tend to think of it as more of a tool since it has a function rather than art, but they have an aesthetic quality that is very nice. And for me, as a trained scientist, I see a guitar as a system that's really interesting in terms of physical study. So we'll talk a lot about that. But I'm what people would call a luthier. A luthier is a stringed instrument maker, and the term goes back several hundred years when lute builders were the big thing, and as lutes became less popular and violins became popular, then even violin makers were called luthiers because they were converted from the lute world. And so I build classical guitars as my specialty, and these are the type of instruments that I make. Classical guitars originated in its most modern form from the 1800s in Spain. They had gut strings back then, 3 treble gut strings, and since the 1950s we now use nylon, which came out of the fishing line industry, and then 3 metal wound basses. And the metal increases the mass so you can reach lower pitches for the same string length and tension. Here's some pictures of my workshop, and my wife says I run my workshop like a lab, and that's probably because my training is in a lab. I'm trained as a research scientist in biochemistry, and while many people think that Lutherie and biochemistry probably have very little in common, I think they really do, and here's why. Biochemists have a fascination with what's known as structure-function relationships. For example, how does this protein's shape make it so good at moving muscles? And in much the same way, I also ask, how does this guitar's structure make it successful at taking the player's instructions and push sound waves to our ears with nuance of frequency and different levels of strength? Both examples are constrained by the rules of physics. And within these boundaries, we must learn how they work if we want to develop them, such as finding cures for diseases or making better sounding guitars. And this is the world in which I live. I live somewhere sandwiched between what the player wants and what the laws of physics allow me to do. And the good thing is that physics is always more predictable than guitarists. So here I am in the middle trying to satisfy both conditions. Well, the reality is that playing the game where the rules of physics define your moves means there are a lot of compromises when you build a guitar. A guitar is much like a tool to the player that uses it to express music. And all the musicians here can think of the important things that a guitar or whatever your musical instrument is, what it needs to be able to do in order to express music, which is such a deep and complex thing. Master musicians can be very picky, and rightly so, because high-level music is often about the nuances that must be communicated to elicit something so emotional. They need an excellent tool to do that job. And if you ask a guitarist, what would you like me to build in your guitar? And they'll typically say, oh, I want it to have good volume, sustaining notes, play in tune, maybe have a variety of tonal colors and easy to play. But turns out that what they really want is something like this. The list can be endless and often it can't be articulated. Subtle things like, I want the notes to have a strong fundamental and a very pleasant and interesting set of overtones. Or I want it to sound good at a distance, such as in a concert hall, but also close up so you can record with a microphone. And we want it to look good. The truth is that most good guitarists will select a guitar based on how few deficiencies it has rather than how many good qualities it has. In other words, the simple knife is not enough. And this is the challenge that I love, though. But the reality is that I can't give them everything they want. Many of their desires are physically opposed, such as, I really want a loud guitar, and I want the notes to last forever. Well, I'm sorry to report that in this universe, there are things like friction and conservation of energy, and that just doesn't bode well for a string that is plucked and not bowed. So my job is to decide on the best compromises and to try to pull out as much efficiency out of the system. And this is why it's important to understand how the system works. And in truth, I'm not exactly sandwiched because it's really this physical reality that envelops all of us in this endeavor. And it's physics that sets the rules. So let's start to look at some structure now. The architecture of guitars is fascinating on its own, such as in this inside view, which few people get a chance to see. And just from this photo on a macroscopic level, we see some important design elements. Inside this room, we have the roof above, which is the soundboard, which is often called the top, which is attached to the strings via the bridge. And when the soundboard vibrates, it will pump air pressure waves to our ears. And while everything works as a system in a guitar, the top is the most important part and is the real transducer of the guitar that has the gears that determine the overall efficiency. And we'll talk in depth about that in a moment. But as you can see, this soundboard and the back, which is actually the floor in this room type of view, are strengthened by beams called braces. And you might think that this room is empty, that there's nothing there, but it's actually filled with a column of air that has mass, which can also vibrate and send pressure waves to the outside via the sound hole, which you see the light coming through. Now remember, I told you that there are many qualities in guitars that we want that are physically opposed, and the example I gave you is loudness versus sustain. Infinite sustain means that a note never dies. Sustain can be crucial for maintaining a melodic line, for example. So we're talking string motion here. And when we first learn about oscillating strings, we usually think about the ideal case, like what we're seeing here, where the ends are fixed to something rigid and heavy, like a wall, where all the string energy gets reflected. It would be something like this. And you already know this is not a good idea. You know you're not going to hear much because the strings can't move the brick, and therefore the brick won't push air to our ears, plus the fact that the strings don't have much surface area to push air to our ear. But this is a great system for sustain because the strings will keep oscillating for a long time because the brick is not draining any string energy. And this is what happens in an electric guitar. That is, if you don't plug it in. You don't hear much because most electric guitars are huge blocks of heavy wood, and it's only because it has electromagnetic pickups that sense the metal strings and convert the movements to current that can be amplified. Now, doing thought experiments at the extremes is good, so let's consider the other extreme. A guitar of our imagination that has a paper soundboard. You can imagine how all the string vibration will easily and quickly transfer to make the paper flap, but then it will be all over because there's no reflectance. In the real world, if we could apply enough tension to this system without it ripping the paper, we'd get a loud but non-sustaining note. And that's the design and character of a banjo. It's a membrane that is stretched around a rim, and when you play it, it's really loud, but very short and almost percussive. But there's a material and design that's somewhere right in the middle, and that's using wood. Through history, wood is recognized as the best solution, such as alpine conifers like spruce and western red cedar. And wood is a really miraculous material. It's light and extremely strong for its weight, so it can resist the tension of the strings so your guitar won't collapse. And it rings like crazy if you activate it. And importantly, it has the right ratio of flexibility and weight to give a good balance between volume and sustain. The downside is that wood is a natural product that comes with a lot of variability in terms of stiffness and weight. And that's even if it's from the same log. But if it was uniform, I could simply build every guitar to the same dimensions. But since they're not, I have to do a lot of compensations in things like thickness in order to produce a consistent sound. Okay, so here's my prototype with a box of air. And then here's the finished product. It's a highly evolved instrument over history. Turning to the soundboard is like the guitar's energy transducer. It's the intermediary between the string energy and the pumping of airwaves to our ears. And it needs to be lightly built and moderately flexible so the strings can easily move it. It's an illusion that they're sturdy, actually. And because they're actually built on the edge of collapse, they're like potato chips with bracing. And here's a soundboard plate without bracing. And it's very thin. It's about 2 millimeters thick at this point. Super flexible, very light. It's about 100 grams. And if I tap it, it's kind of resonant, makes some very nice sounds. It has a fundamental pitch and some overtones that you can hear, but still pretty raw. And the flexibility is important because that determines a lot of how the pitches come out, and we'll talk about that. Here's a soundboard that has bracing, and it's much stiffer. It's about twice as stiff, even though the braces don't add much more weight to it. And if I tap it, because it's stiffer, the pitch is higher. And the braces give it more focus, but a higher pitch. The braces, you could see, have directionality, and I can use that directionality to change the character of the top in terms of how it moves and how it sounds. And we'll talk more about that too. Now, braces are an incredible invention because they add a lot of strength without adding much weight, which is why we use them in things like floor joists. Engineers know that it saves a ton of weight to add a bunch of beams to give strength instead of having to increase the thickness of the floor itself, which would get so heavy that it becomes weak again. So on a top like this, I can double the strength of the plate and only add about 15% more weight in braces, and I'll take that trade-off any day. The braces are glued to the soundboard on this deck, and instead of using clamps, I use an old method of jamming sticks between the roof of the deck and the braces. And here's another classic engineering move. I've added a tiny bit of arching where the braces meet the soundboard. And this arching also adds stiffness without adding any weight. And you already know how arches are fantastic in things like bridges. And the Romans definitely knew how to take advantage of the incredible strength of arches. But you can overdo the stiffness, and that results in a very aggressive sounding guitar that is maybe too treble oriented and has some very annoying sounding overtones. I shave the braces to really fine tune the stiffness in different areas. I like to think of this process as carving away stiffness to introduce more flexibility. And by now you're probably getting the picture that my whole job as a luthier is to control stiffness and weight and spatial distribution of those two things. I'm trying to achieve the right balance of the flexibility in the top plate and marrying it with the right amount of bracing. And this all determines the eventual sound character of the guitar and how it will perform in a large range of pitches that the player is going to instruct the guitar to play. So with our energy transducer soundboard finished, then we close the top, gluing it together with a million clamps, and then we have a completed body fully capable of resonating if we energize it in some way. And it doesn't even have to be with strings. And this is where I challenge you to stick with me, because what follows is what people might call the whole enchilada. If you get this last part, you'll get the real essence of building musical instruments. So if you're ready, let's go. Now with this completed body, most of the acoustic capabilities are pretty much baked in if we activate it with energy. Of course, if we added the neck and strings, we could activate it with very specific string energy. By specific, I mean the player will select the note on the fingerboard, and then that will specify the fundamental frequency and all the associated sets of higher frequency overtones depending on how the player strikes the string. But without a neck, it's still acoustically very interesting because I can activate it by tapping and listening to the output, similar to how you would ring a bell and listen. Unlike the case where the player plays the string with a specific note, by tapping it with a hammer, I can activate almost every possible pitch the box can radiate. It won't sound great, but it will radiate a large number of pitches. In other words, it's showing me its potential to support each note on the fingerboard once it's on. And some notes will be better than others, and it's my job as a builder to equalize that potential. So here's the completed box, and I've got this hammer, and I'm going to tap it in different places and listen. Now, I can hear a lot of different pitches, but I can't hear all of them. I just can't, my brain can't resolve all of the pitches that are coming out of this soundboard. But if I have a microphone and a laptop, I can use that to pick up the vibrations off of the box and then use an algorithm to tell me what pitches are being heard. And here's the output with the frequency on the x-axis and the relative strength of the output on the y-axis. The peaks that you see are the different pitches that the microphone heard when we tapped. It kind of looks like a big mess of peaks all jammed together. And it looks very different than when you tap, say, a bell, which is tuned to a certain pitch and radiates a very ordered set of frequencies. But for tapping a guitar, we see a big pile of peaks jammed together so that there's a lot of area under this curve and no gaps that hit zero. And having a lot of area under this curve is important, and let me show you why. Let's consider a situation where I take my guitar and I play A220. Sounds like this, and the computer hears this. Here's the fundamental at 220 hertz plus some overtones. If there's no potential for the box to support these frequencies, you won't hear them because the box physically can't vibrate at these frequencies. But fortunately, in this guitar, they do, and this relative mix of fundamental plus overtone sounds really pleasant. So bringing back the box's potential in the lower panel, you can see what needs to happen. There has to be area under the curve in the bottom panel at the pitches being played by the string. The player and the string instruct the frequencies, and the question is, can the box vibrate at that frequency to obey the string's command? And if the answer is yes, you will hear those frequencies. Let's consider a hypothetical case where there's a gap in the box's output potential shown in red down at the bottom, meaning that the soundboard just can't vibrate at that frequency to generate the sound. Maybe the top is too stiff or it's too heavy. And the sound profile in the top panel might look like this in red. The relative abundance or orchestration of the different overtones will have changed, and we would hear what we would call a different tonal color for that note. This is, in essence, how different guitars can wind up sounding different depending on the landscape of the guitar's output potential in that lower panel. And this is the whole enchilada. My job as a luthier is to move these peaks left or right, or try to equilibrate the heights of these peaks to give a smooth landscape which results in a smooth sound. And it all comes back to manipulating spatial distribution of stiffness and weight. My sonic recipe must take into account things like material choice, material thickness, and bracing size and direction. And if that was the whole enchilada, then what I'm going to tell you next is the super enchilada with all the fixings, and then we'll end our session. Resonances are movements in vibrating objects that happen at high efficiency at specific frequencies. In other words, it's easy to get the top to vibrate at those frequencies. They are all those peaks you saw. So here's a video that I made for you last night to show you how this works. Ernst Chladni was a German physicist and musician who is considered the father of modern acoustics. In the 1780s, he wrote a treatise on how vibrating plates move. You probably know of his famous demonstrations where he sprinkled sand on metal plates and got the sand to move by activating the plate with a violin bow. The sand settles in lines called nodes because those are the boundaries where the plate is motionless, whereas the vacant areas indicate areas of motion. Today we know that these patterns are formed the strongest when the plate is activated at resonant frequencies, and we refer to them as modes of vibration. But back then, Chladni's contribution was a glimpse into a completely unseen and poorly understood process of how plates move. Fast forward to today, and we know that we can replicate Chladni's experiments with our guitars, but instead activating them through space with sound waves, which physically are air molecules. You've already experienced this phenomenon when you're holding your guitar and it starts to vibrate when someone talks to you or plays in front of you. All of this is now made easy with a computer directing sound to a speaker, and this is what we're going to do. Let's try some Chladni analysis to look at some top movements, and I think it'll help you understand what these resonance peaks mean physically. So what I have is my guitar body, I have some tea leaves to act as an indicator, I have my laptop which can run pure sine waves of any frequency that I want, and then I have my Bluetooth speaker to send these sound waves, and I have some hearing protection. And let's start at this big peak at 178 hertz. And for you guitarists out there, 178 hertz is near F or F sharp on the 4th string. So if you're playing any notes in that vicinity, then this is the top movement that would be predominantly made when you play those notes. What's happening at this frequency is a relatively simple movement where the big middle area moves up while the periphery moves down, and then it flips where the middle area moves down and the periphery moves up. And this repetitive flipping happens at 178 times per second. Let's move up in frequency to 211 hertz, and you'll see that the patterns start to get more complex as we go to higher pitches. Moving up again to this resonance peak at 322 hertz. Now I want to show you how braces can dramatically alter the movement of the top depending on direction. Of course, there's already bracing underneath this top, but I'm going to tape an additional brace which adds stiffness. And let's try it again at 322 hertz. Notice what happens when the brace directly opposes the flipping action of the sectors. I can almost completely kill the movement at this frequency, which will have an effect on the sound because notes near this frequency may not be well represented if we tried to play them. But if I turn the brace 90 degrees, what do you think will happen? It turns out not much at all because the direction doesn't oppose the flipping motion of this resonance. And now you can appreciate how bracing is not only a structural element, but also a device to control top motion and therefore sound characteristics. So we've come to the end of today's session, and I really want to thank you for sticking with me because I presented and challenged you with a lot of complex material. And it's okay if you didn't grasp everything because guitar builders have been building guitars as we know them for about 200 years at least. And they certainly didn't understand all the underlying physics. But I do know that the concepts and the analytical tools that I showed you today do help me to build a better guitar in the sense that I can make predictions and know how the guitars are going to sound or fine-tune them long before I ever string them up. So here are just a few things that I hope you take with you. Wood is a great material for acoustic guitars. It's light but strong and gives good compromise between volume and sustain. Bracing provides good stiffness for very little weight. It provides strength to resist collapse, but is also a good tool to control sound. A guitar needs many resonances to support the frequencies instructed by the player and the string. You can think of each resonance like a gear in a car. You need a collection of gears to go different speeds, but in our case, it's to drive different pitches. Each resonance corresponds to a motion. And finally, the builder can change the resonances to change the sound. Before I leave you, if you're interested in exploring more, there are 2 places you can visit. My website, garrettleeguitars.com, where you can hear what the guitars sound like played by some world-class players. In my YouTube series called Lutherie Demystified, where you can learn more about the craft of guitar building. So thanks again. It's a real privilege to spend time with you. So why don't we answer some questions now? I hope you enjoyed that presentation as much as I enjoyed putting it together and working with the students. It wasn't meant to be comprehensive, but I wanted to put together an introduction of the world of Lutherie and how luthiers work with players and try to satisfy the rules of physics. And in upcoming videos, you'll see me further characterize more thoroughly the resonant peaks in that impulse spectrum. So I will see you on those videos.